All right, the final stand, the last two questions of the review. I know this is kind of a lengthy review, but there's just a lot to look at. So let's see how we can do on those last two. So question 16 should be a nice, easy one. I gave a graph, and I just want to know what the equation of that graph would have to be. And I think we can tell right away that there's a little S-curve happening at -2. So we all know that's going to be an x plus 2 cubed. We also see a little parabola or a little bounce happening at 0, so that's going to be an x squared. You could say x minus 0 squared, but that feels kind of funny. And then, of course, over here at the end, there is an x minus 2 squared. Now, the only thing is, when we do this, is I don't know what leading coefficient there could be, because if I put an a there, it's going to describe every graph that has this shape, no matter how tall or how short it is. But since I actually gave you one very, very special value, I can not only find the general form, I can find the specific one. So if I plugged in 15 for f, and I plugged in 1 for x, 1 plus 2 is 3, cubed is 27, 1 minus 2 is -1, -1 squared, of course, is 1. So when I put all that together, I've got 15 is equal to 27a, or a is 5/9, which means I didn't find a graph, I found the polynomial that worked, which was 5/9 of x squared times x plus 2 cubed times x minus 2 squared. That's not just a polynomial, it is the polynomial. Now on number 17, this looks horrific because it is. And then, so I kind of asked you some questions that says, hey, let's find all the possible rational roots, which of course, as a student, you should be like, well, 1, 2, 4, 5, 8. Oh my gosh, how many numbers go into 640? If you do a factor tree on that, it's nuts. So I literally meant just kidding. The reason I said kind of is I do want you to know how to do that if the numbers were more reasonable. But this one has so many options, it's just ridiculous. So we're just going to talk about a couple of little things and then put this one to bed. We're never going to actually find all these roots. So Descartes said, let's count sign changes. And I see one here, and one there. So for a total of 1, 2, 3. So Descartes didn't stop by just saying 3 positive roots. He said 3 or 1. And again, this only talks about real roots. Now, when we look at h of -x, we would take a negative to the 7th, which is a minus, a negative to the 6th times an additional negative, a negative to the 5th times a positive, a negative to the 4th times a positive, a negative to the 3rd times a negative squared times a negative, and then a positive times a negative, and then a positive. Well, that's a lot of signs there because it's the 7th degree, and I saw 1, 2, 3 sign changes there. That's not possible. Let me try that again, because 3 plus 3 would be 6, and this is a 7, so that can't be. So let me see. A negative is going to give me a negative times a negative. Okay, that is definitely still negative. This one, a negative to the 5th is negative times a positive. A negative to the 4th times that, a negative to the 3rd times that is positive. A negative squared times that is negative. A positive times a negative is negative, and that's positive. That still feels good. And so I saw 1, 2, 3. So this is 3 or 1 positive. So again, I'm just showing you what happens. Sometimes we make mistakes. So let's see, did I make a mistake in my initial analysis? I saw 1 sign change here. Oh, I missed 1 here, didn't I? So that should have been 4. Let's fix that. That should have been 4 or 2 or 0. But notice you could see something that I was doing. I was seeing what happened, because if it's 4 and 3, that's 7. If it's 4 and 1, that would be 5, which would leave 2 imaginaries. Or it could be 0 and 1, which would leave 6 imaginaries. That's okay, because of the conjugate roots theorem, they have to come in pairs. So you cannot ever have an even number of complex roots that are left over that have imaginary components. Now, in terms of upper and lower bounds, Pretty simple little idea. The lower bound looks for alternating signs, and it turns out the first one that does this is -3 right in here. It goes plus minus across. So my greatest lower bound is -3, so when you're looking, we don't even bother to look up here for roots. My upper bound just looks for positives, and unfortunately there's some pesky little negatives that keep hanging on because of the size of that 53 there. So as it turns out, I needed to go all the way up to 9 to get that upper bound. Now, finishing it up, h of 4 is a simple coordinate. H of 4 was 0. Of course, that's something we should look for because that's going to lead us to an actual root, which is going to make us be able to factor this down at least a tiny little bit. And then the last thing I was going to say is that I know by the intermediate value theorem that right in here, because it went from a negative to a positive, somewhere between -1 and 0, there must in fact be a root. Now, is it possible there's some other ones in here? The answer is yes, but that's literally the only perfect sign change I see. And that's going to be kind of the end of the review. Hopefully that was helpful and not too long. All right, thanks. I'll see you back in class.